Good afternoon, everyone. Welcome back, and thank you for joining us. And we're glad that you're with us. I'm Steve.
Yep, we appreciate you listening, and I'm Scott. And
We are the Science and Technology Channel, Backyard Musings.
yep, and we're talking about this morning. We talked about a favorite topic of Steve's, and now we're talking about a favorite topic of both of ours, and that is space. And we talk about that a lot. So
Yes, sir. And I learned something new on this. Jupiter and Saturn host strikingly different polar storms, despite being similar giant planets. I didn't know that Saturn was as big as Jupiter. I didn't know that. I mean, maybe a little bit smaller, but about the same size. I didn't know that. And scientists have long wondered why. New simulations suggest the answer may lie deep below the clouds. Spacecraft flybys have given scientists a front row seat to some of the strangest weather in the solar system, especially over the poles of Jupiter and Saturn. And so when I first read this, I was like, well, I mean, you look at our Antarctica pole, the southern pole, the seas in the lower 40 is what they call them for the latitudes. Those seas are very tumultuous, very rough. Like I think it's Magellan's Passage, or is it Drake's Passage around Chile? That is really dangerous. I mean, it's like a 50-50 shot whether your ship is going to sink because of the storms. Wow. Yeah. Saturn's North Pole is dominated by one giant storm that traces out a surprising hexagon, while Jupiter's polar region looks more like a tightly packed cluster, a central vortex ringed by 8 smaller ones. Would you like to know more?
I think it's all about the rings.
Yeah.
Saturn's got the rings, and Jupiter, it's got the moons, right?
Maybe. Yeah, maybe.
I don't know. Because Jupiter has 4 moons, is that correct? 4?
Oh no, Jupiter has like 50 or 60. Yeah.
The 4 moons that are distinct.
Before the Galilean moons that we can see.
Yeah. I got to look at those the other day at my grandkids' science and technology expo thing at the Lewis Center. So anyway, that contrast is hard to dismiss as a surface level quirk. Jupiter and Saturn are similar in size, but largely from the same gases, yet their polar storms settle into very different long-lived arrangements. A team at MIT argues the answer may be hidden below the cloud tops. In work published in the Proceedings of the National Academy of Sciences on January 20th, 2026, the researchers used computer simulations to watch orderly vortex patterns emerge from random churning on a gas giant. Depending on the conditions, the simulated winds either merged into a single dominant polar vortex like Saturn's, or stabilized into multiple large circulations resembling Jupiter's.
The key divider was a trait the team calls the softness of they're calling it softness of a vortex's base, which reflects a planet's interior composition. They described each vortex as a spinning cylinder extending through many atmospheric layers. And I'm picturing this in my mind, this cylinder, If the lower portion sits in softer, lighter material, the vortex hits a growth limit, leaving room for several smaller storms to coexist. If the base is harder and denser, the vortex can expand far more, swallowing nearby vortices until one massive system remains.
That link between what happens deep inside a planet and the patterns seen from above, a new twist to images returned by missions like Juno at Jupiter and Cassini at Saturn. If the model is right, the geometry of a planet's polar storms could act as a clue to what is happening beneath the clouds, where direct measurements are far harder to obtain.
Quote, our study shows that depending on the interior properties and the softness of the bottom of the vortex, this will influence the kind of fluid pattern you observed at the surface, says study author Wan-Ying Kang, assistant professor in MIT's Department of Earth, Atmospheric and Planetary Sciences. Continuing the quote, I don't think anyone's made this connection between the surface fluid pattern and the interior properties of these planets. One possible scenario could be that Saturn has a harder bottom than Jupiter. The study's first author is MIT graduate student Jiaru Shi. We need to get a spacecraft to land in there and take measurements and shoot those measurements back.
Yep. Kang and Xi's new work was inspired by images of Jupiter and Saturn that have been taken by the Juno and Cassini missions. NASA's Juno spacecraft has been orbiting around Jupiter since 2016, and as Steve says, we need to land something on that planet, right? And has captured stunning images of the planet's north pole and its multiple swirling vortices. From these images, scientists have estimated that each of Jupiter's vortices is immense, spanning about 3,000 miles across, almost half as wide as the Earth itself. Shouldn't that be our immense?
Should it be what?
Shouldn't that be each of Jupiter's vortices are immense?
Yeah. Oh,
Well,
yeah.
Anyway, I'm not. Yeah, I'm definitely not an English major. So
the Cassini spacecraft, prior to intentionally burning up in Saturn's atmosphere in 2017, orbited. That would have been a perfect time to take measurements while it's burning up. Orbited the ringed planet for 13 years. Its observations of Saturn's North Pole recorded a single hexagonal-shaped polar vortex, about 18,000 miles wide.
Wow.
People have spent a lot of time deciphering the differences between Jupiter and Saturn, she says. The planets are about the same size and are both made mostly of hydrogen and helium. It's unclear why their polar vortices are so different.
Xi and Kang set out to identify a physical mechanism that would explain why one planet might evolve a single vortex while the other hosts multiple vortices. To do so, they worked with a two-dimensional model of surface fluid dynamics. While a polar vortex is three-dimensional in nature, the team reasoned that they could accurately represent vortex evolution in two dimensions, as the fast rotation of Jupiter and Saturn enforces uniform motion along the rotating axis. Man, I bet you they were giddy when that was going on. Yeah.
Got that slide rule out.
Yeah.
Well, in a fast rotating system, fluid motion tends to be uniform along the rotating axis, Kang explains. So we were motivated by this idea that we can reduce a 3D dynamical problem to a 2D problem because the fluid pattern does not change in 3D. This makes the problem hundreds of times faster and cheaper to simulate and study.
Following this reasoning, the team developed a two-dimensional model of vortex evolution on a gas giant based on an existing equation that describes how swirling fluid evolves over time. The team applied their two-dimensional model to simulate how fluid will evolve over time on a gas giant under different scenarios. In each scenario, the team varied the planet's size, its rate of rotation, its internal heating, and the softness or hardness of the rotating fluid, among other parameters. Then they set a random noise condition in which fluid initially flowed in random patterns across the planet's surface. Finally, they observed how the fluid evolved over time, given the scenario's specific conditions.
Over multiple different simulations, they observed that some scenarios evolved to form a single large polar vortex like Saturn, whereas others form multiple smaller vortices like Jupiter. After analyzing the combination of parameters and variables in each scenario and how they related to the final outcome, they landed on a single mechanism to explain whether a single or multiple vortices evolve. As random fluid motions start to coalesce into individual vortices, the size to which a vortex can grow is limited by how soft the bottom of the vortex is. The softer or lighter the gas that is rotating at the bottom of the vortex, the smaller the vortex is in the end, allowing for a multiple smaller scale vortices to coexist at a planet's pole, similar to those on Jupiter.
Conversely, the harder or denser a vortex bottom is, the larger the system can grow, to a size where eventually it can follow the planet's curvature as a single planetary scale vortex, like the one on Saturn. If this mechanism is indeed what is at play on both gas giants, it would suggest that Jupiter could be made of softer, lighter material, while Saturn may harbor heavier stuff in its interior.
Quote, what we see from the surface, the fluid pattern on Jupiter and Saturn may tell us something about the interior, like how soft the bottom is, she says. And that is important because maybe beneath Saturn's surface, the interior is more metal enriched and has more condensable material, which allows it to provide stronger stratification than Jupiter. This would add to our understanding of these gas giants.
Okay. So,
Take their word for it until we can get a spacecraft down there.
And I guess I didn't realize that, is that Cassini that was vaporized?
Yeah.
Burned up
in the atmosphere.
So kind of gave its all for the study. But I guess that was planned, right? That was all part of the plan?
Yeah, probably did. They didn't have a way to change the orbit, and it just kept getting closer and closer and closer until it burned up.
Yeah. Oh, well.
The 13 years, it gave its final measure. 13 years of data.
Yeah, that's pretty cool. So anyway, great day today.
Thanks for joining us. We appreciate it.
See you this afternoon, or see you tomorrow. Take care. Thanks, everyone.